in approximation methods for stationary states. Today we are going to see the concept of the third and the last approximation method to discuss the problems of quantum mechanics by approximation methods, particularly in case of a stationary state system. And in fact, before this lecture, we have seen the two methods. First of all, we have discussed perturbation theory for the degenerate and non-degenerate state of the system. And after that, we have learned about variational principle. Now, today, our aim is to discuss the last approximation method for stationary states, and that is actually the WKB approximation. You know, this WKB approximation is actually Wenzel, Kramers and Broglie approximation. So, we will learn in this lecture on this WKB approximation that when this method is suitable for solving the problem and what will be the solution of WKB potential, okay, and what is the criteria for the validity of this WKB approximation. All these things we will learn in this lecture. In fact, whenever you talk about WKB approximation or WKB method, definitely you should think that when this method will be useful, when this method will be suitable for applying in a physical problem to solve it. Actually, it is seen that this method is particularly useful for approximate treatments of the systems with slowly varying potentials. Mark it. When the potential varies slowly, then this method will be appropriate. When you say that potential is varying slowly, what does it mean? It means you are talking about the potential which remain constant, almost constant you can say, over a region of the order of de Broglie wavelength. It means if you consider that this is a region, okay, between these two boundaries, and this distance is of the order of de Broglie wavelength lambda. And in this region, the potential V is varying slowly. It is almost constant. Then in this situation, the WKB approximation can be applied. This will be useful for approximating the for the approximation method to be applied. In fact, why we say that if the potential is almost constant or the potential varies slowly in a region of the order of de Broglie wavelength. In fact, you know, for a classical system, this de Broglie wavelength is very small, negligibly small. It almost tends to zero. So, if you consider that the potential is varying and in a region which is of the order of de Broglie wavelength, it means in this case, we are talking about the classical situation, okay? Because in the case of classical system, you know, this property is always satisfied because the wavelength of classical system approaches to zero. So this is the reason that this WKB approximation is also called semi-classical approximation. Okay. So I have mentioned here, you can see that in this case, the classical system, this property is always satisfied since the wavelength of a classical system approaches zero. because when you talk about lambda of a classical system, this lambda will be h over mb. Okay, and since for a classical system this m is large, h is the Planck's constant, which is of the order of 10 to the power minus 34 meter. So this lambda will be negligibly small for a classical system. Okay, and so that we can say that this WKB approximation is viewed as a semi-classical approximation. Okay. In fact, this WKB method was first of all given by a famous mathematician Harold Jeffreys in 1924. Okay. Since Harold Jeffreys put forward this approximation method at first in 1924, so it will be superior to say that this method is JWKB method. It means Jeffrey, Wensdale, Kramers and Brillouin method. That will be more appropriate. Okay. So, in nutshell, what just I have introduced you, that this WKB approximation is actually applied only in the problem in case of which the potential will vary by a slow rate or potential remains almost constant in a region whose width is of the order of the Broglie wavelength. Okay? So this approximation actually transforms our problem from quantum mechanical problem to classical problem. So this is called semi-classical approach or semi-classical method or semi-classical approximation. Okay. Now let us see what is the basic theory or what is the general formalism of this WKB approximation. Okay. And for this we consider the motion of a particle, let us say of mass m, in a time independent potential V of r. This is a stationary potential. Okay. And if you consider that a particle of mass m is moving in a time independent potential V of r, then you can write the Schrodinger equation for this stationary, corresponding to the stationary state of this particle. And you know, in 3 dimensions, the Schrodinger equation will be then written for this particle as del square psi of r equal to 2m over h bar square e minus v of r psi r equal to 0. Okay. Now, in fact, you know, if a particle is a free particle, it means its potential V is 0. Then its momentum, you know, is given by root over 2me, where E is energy of the particle. You know it. But if a particle is moving in a region where the potential is V, not 0, then what is its momentum? Its momentum is given by a square root of 2m times E minus V. Okay. So in this expression, this 2m times E minus V of r, this is just a square of the classical momentum of the particle at the position r. So instead of this 2m times E minus V of r, you may write P square of r. Okay? Where this P of r, as I have told you, this is equal to this much, and this is actually the classical momentum of the particle at the position r. So the Schrodinger equation in terms of this momentum, you may write as I have written in this equation 1. Okay. Now, if you consider that the particle is moving in a region where this V of r is constant, okay, V of r is constant, then you can see if V of r will be constant, then this P will be also constant, and this equation will be then simply equal to del square psi of r, okay, and plus P square over h bar square, P square over h bar square. This will be just a constant, okay, and so you can write at the place of this P square over h bar square psi. In fact, this equation you can see is just equation of a simple harmonic motion. Here the solution of this equation psi of r will be definitely oscillatory. This will be definitely oscillatory, and what will be its solution? As psi of r in this condition will be of oscillatory nature, so you can write its solution in terms of the sine function or cosine function or in this exponential form. Okay? Here's if V of r is constant, then P square over h bar square. This is P over h bar whole square. Okay? So this is at the place of the frequency. As you can see, the equation of SHM, you write d2 psi by dt square plus omega square psi equal to 0. And you know, in this condition, the solution of this second order ordinary differential equation psi is of oscillatory nature. And therefore, you write its solution in this manner, psi equal to a constant A e to the power plus minus I omega t. Okay. Here at the place of omega, there is P divided by h bar. Okay, P divided by h bar. So if V of r is constant, then the solution of this equation number 1 can be written like this. Okay. But how does one deal with those cases where V of r is not constant, okay, but V of r is varying with respect to r, or on variation of r, variation of position, the potential varies? Then how this problem will be dealt? Actually, this WKB method provides an approximate treatment for systems whose potentials, while not constant, are slowly varying functions of r. Okay? That if V of r will vary fastly, rapidly, irregularly, then you can't apply the method of WKB approximation. WKB method can be applied if this potential V of r varies slowly with r. Okay? Then we can actually apply the WKB approximation technique. Okay? It means if you are saying that V of r is almost constant in a region which extends over several de Broglie wavelength, let us say lambda. It means you are talking about a region which is, let us say, of width d equal to n lambda, okay, where lambda is the de Broglie wavelength. Then, in this region, if V of r is varying slowly, you can use the technique of WKB approximation. Okay? And you know, this de Broglie wavelength, lambda is given by h over p, where p is the linear momentum of our particle, h is Planck's constant. But just we have seen that this classical momentum P is given by a square root of 2m times E minus V of r. Okay? This is the angular momentum. Okay? Actually, in essence, the WKB method consists of trying solution to this Schrodinger equation, which I have defined here in this equation 1. This is your equation 1. Okay? In this manner, we seek the solution of that equation 1, which is actually Schrodinger equation written in terms of the momentum P. We want to its solution in this form. Psi of r is equal to A of r times e to the power I s of r over h bar. Here actually this s represents the phase and this A of r represents the amplitude. Okay? And this psi of r is called WKB wave function. Okay? In fact, the amplitude A of r and the phase S of r both are real functions of r. Okay? But they are not known, they are unknown. And so, first of all, we will try to obtain the value of A of r and S of r. Okay? And for this, let us use this equation 2 in equation 1. You can see, what is your equation 1? The first term in equation 1 was del square psi of r. But you can see from equation 2, psi of r is this much plus p square of r over h bar square psi of r. Again, at the place of psi of r, we can write A of r e to the power ISR over h bar. And that's equal to 0. Okay? Actually, when you will solve this equation, operating this Laplacian operator on this function, then you will get a complex quantity. Actually, I have here skipped some of the steps in calculation because my aim is to provide you this video in such a manner so that you can directly write the answer regarding this WKB approximation in your examination of MSc level, academic level. Okay? So I have actually skipped some of the useless steps. Okay? And only those steps which you can do yourself. So when you will watch this video, definitely take a pen and notebook and try to solve these equations where I have skipped. Okay? So when you will apply this Laplacian operator, you will get a complex quantity, and if you will separate the real and imaginary part of that complex, you will get its real part is this much. Okay? And its imaginary part is this much. You will get. Okay? But you know, if a complex is 0, definitely its real and imaginary parts are separately equal to 0. You know it. And therefore, we can equate the real part of this complex and its imaginary parts separately to 0. So let us see. This is the real part of this complex, and that will be equal to 0. Now, you know, h bar is of the order of 10 to the power minus 34. You know, Planck's constant is of this order. So h bar square, this will be of the order of h bar square, this will be of the order of 10 to the power minus 34 times 2. It means 10 to the power minus 68. Okay? So you can think that the term containing h bar square will be definitely much smaller than del s square or p square, and therefore you can neglect this term containing this h bar square in here. And so when you will neglect it, then your result will be del s square equal to p square. But you know, p square is equal to 2m times e minus v of r. Okay. Again, we can equate the imaginary part of this complex to be 0. So this is the imaginary part of this complex. You can see it here. This is the imaginary part. Okay. And therefore this will be also equal to 0. Now, actually, to illustrate the various aspects of the WKB method, let us now consider the simple case of the one-dimensional motion of a single particle. Okay? And so, if you consider the one-dimensional motion of a single particle, then you have to write the one-dimensional equivalent of these two equations. That is equation number 4 and equation number 5. You know, here in LHS there is gradient of S. Gradient is a three-dimensional operator, but its one-dimensional equivalent will be what? That will be ds by dx whole square. This is one-dimensional equivalent of del s whole square. And if you will find the value of ds by dx, then that will be equal to a square root of p square of x or a square root of this 2m times e minus v of x. Okay. So the one-dimensional equivalent of this equation 4 is given as ds by dx equal to plus minus a square root of 2m times e minus v, or it is equal to plus minus p of x. Okay. In fact, I have taken here this plus minus sign because this change in phase, that is ds, may be positive or negative. Phase may be increase or it may decrease. Okay. And again, when you will simplify this equation 5 and take its one-dimensional equivalent, then this equation 5 can be written as 2 times d dx ln a times px plus d dx px equal to 0. Okay. Now we can solve these equations, that is equation number 4a and equation number 5a. For solving equation 4a, you must integrate it and see this equation, and let us try to integrate. So the integral of ds will be s, and that will be equal to integral dx times this much with plus minus sign. Or since ds by dx is equal to plus minus p of x, so sx will be equal to plus minus integral of p of x dx. Okay. Now again, this equation, which is the one-dimensional equivalent of equation 5, see this and you can check that this result can be written in this manner: d dx operated on 2 ln a plus ln p of x, and that is equal to 0. Now, when you will integrate this equation, you will get a of x equal to c over a square root of p of x. Here c is actually an arbitrary constant. This is in fact integration constant. This is integration constant. Okay. So in this way we have obtained the value of s of x in equation number 6 and the value of a of x in equation number 7. and therefore the phase S of x and the amplitude A of x of the WKB wave function psi of x equal to this much. This is actually the one-dimensional equivalent of this equation, psi of r, which we have mentioned in your second equation. Psi of r equal to A of r times e to the power I S of r over h bar. Okay. Actually, one-dimensional equivalent of this equation is this, and this function is called WKB wave function, and S is here the phase of the WKB wave function, and A of x is its amplitude. And how A of x and S of x, which are the amplitude and the phase of the WKB wave function, are defined in equation 6 and in equation 7. Okay. So finally, now you can obtain the two approximate solution of the Schrodinger equation which I have defined in the beginning. And what will be that solution? That will be given by psi plus minus of x equal to c plus minus over root px. This is at the place of A of x and c. And S of x, you can see this is plus minus integral p of x dx. So when you will substitute this value defined in equation 6 at the place of this S of x, then this exponential factor will be e to the power plus minus I over h bar integral for x px dash dx dash. Here you cannot write x dash, that will be also right. It means we can write this is integral over x px dx. Okay. But since here we will substitute the limits for x. So the variable has been changed, but you know the value of a definite integral does not depend on the variable. It depends on the nature of the function. Integral of t between 0 to 2 and integral of x between 0 to 2. Both will be equal or unequal. Answer will be equal. Okay. So if you will write x dashed instead of x, answer will be not different because it is a definite integral. Okay. So assuming the two values of s of x, that is positive and negative value, there will be two solutions of Schrodinger equation, one for the positive phase and another for the negative phase. Okay. And correspondingly, this integration constant c will also have two values for the plus positive value of sx and for the negative value. Okay. In fact, you can see this equation that and it is clear from this equation 8 that the amplitude of this wave function is proportional to a square root of p of x. You can see its amplitude is c plus minus root over p of x. This is the amplitude. And this amplitude, in this amplitude, you know, this c plus minus is constant. So the amplitude is proportional to 1 over root px. Okay. But you know, from the Max Born interpretation of wave function, that actually the square of the modulus of amplitude actually gives the probability density P. So what will be the square of this amplitude? This will be a square of c plus minus and divided by p of x. Okay. So the probability density or probability of finding of particle between x and x plus dx, that will be inversely proportional to px, or you can say proportional to 1 over px. Have you understand? According to Max-Born interpretation, the probability density is equal to a square of the modulus of probability amplitude. Okay? And so this probability, the probability of finding of a particle in the region between x and x plus dx, this will be proportional to 1 over px. Okay? Actually, this is what we expect for a classical particle, because the time it will take to travel a distance dx is proportional to the inverse of its speed. If you consider that at this point x particle is at a time t, and at this position x plus dx, the particle is at a time t plus dt. Okay? Then what will be this time dt? Dt will be dx divided by v, dx by v. And if you will multiply by the constant factor m in numerator and denominator, this will be m dx by mv. And mv is the momentum. So you can see that actually the time taken by the particle covering this distance dx is proportional to momentum of the particle. And that is, therefore, this fact actually verifies that the probability of finding of the particle in this region will be proportional to 1 over p of x. Okay? So actually this quantum mechanical result is validated by the classical concept. Okay? And that's why I have told you that this is what we expect for the classical particle, because the time it will take to travel a distance dx is proportional to inverse of its speed or its momentum. Okay? So now actually we can now examine two separate cases corresponding to E greater than V of x and E less than V of x. Okay? First, let us consider the case E greater than V of x. Actually, this case, when you say E is greater than V of x, this is actually classically allowed region. Why it is classically allowed? You can check. You have seen that momentum of the particle is given by a square root of 2m times E minus V. Since we are considering E is greater than V, so this will be a positive real quantity, or you can say P will be real. And classically, in classical mechanics, momentum is always real. And if momentum is real, you can also see that this E minus V is actually the measure of kinetic energy. E is total energy, V is potential energy. So E minus V measures the kinetic energy. And since our assumption is E is greater than V, so E minus V, which is kinetic energy, that is positive. And according to classical mechanics, kinetic energy is always positive, never negative, never imaginary. So in this condition, you can say that this E greater than V of x is classically allowed region, because in this condition, kinetic energy is positive and P of x is real. So it is called classically allowed. It means this region actually permits the particle to be moving through it, okay, in classically. Actually, in this condition, What will be actually the solution of the Schrodinger equation which we have defined initially in equation number 1? Okay. Actually, the general solution of the Schrodinger equation defined earlier will be in this condition a combination of the wave function psi plus of x and psi minus of x. It means you have to take the positive momentum and the negative momentum, and therefore the solution of Schrodinger equation is given by psi of x. This psi of x here will be called WKB wave function, and this will be given by c plus over a square root of p of x times exponential raised to the power I over h bar integral for x px dash dx dash, and plus c minus over a square root of px e raised to the power minus I over h bar integral for x px dash dx dash. Okay. Actually here p is positive. Okay. So this will be the solution of the Schrodinger equation, and this psi of x, which is a combination of psi plus of x and psi minus of x. This is actually called the WKB wave function. Now, what will be the second case? In second case, we consider E less than Vx. When you say E less than Vx, then you know E minus V. This will be less than 0, that is negative. And therefore, a square root of 2m times E minus V, what will be this? This will be imaginary, because a square root of a negative number, you know, is imaginary. And E minus V, you know, is the measure of kinetic energy. So in this condition, you have to say that kinetic energy of the particle is negative and its momentum is imaginary. Are these two statements classically correct? Classical mechanics allows such fact? Answer is no. In accordance with classical mechanics, kinetic energy is never negative and momentum is never imaginary. So this region where E will be less than V of x, that is called classically forbidden region. It means in accordance with classical mechanics, the particle cannot move in that region. That is forbidden region for that particle. Okay. So this situation, or E less than V of x, where this situation exists, that is called forbidden region, classically forbidden. It means this region does not permit the particle to move in classical way. Okay. And in this condition, the exponents of the solution of Schrodinger equation will become real. But when in that condition, you have to take the modulus of this E minus P, modulus, then it will be positive. And therefore, the WKB wave function, or the solution of the Schrodinger equation for the classically forbidden region, we will write in this manner: psi of x equal to c dashed minus over a square root of modulus of px, don't take its minus sign, and e to the power minus 1 over h bar integral over x integral with respect to x p modulus of p of x dash dx dash, and plus c plus dashed. Actually, I have changed the symbol of the constants. A square root of mod of px times e to the power 1 over h bar integral this much Okay. So this equation 9 you can see here. This equation actually gives you the wave function in the classically allowed region, while this equation 10 gives you the wave function in the forbidden region. Okay, in the forbidden region. But what about the structure of the wave function near the region where E is almost equal to V of x? Okay, where E is almost equal to V of x, what will be the structure or what will be the wave structure of the wave function in such a region? Actually, at all those points where E and V are equal, let us consider there are several points, let us say xi, where I equal to 1, 2, 3 and so on. These are the points where E is equal to V of x. If E is equal to V of x, then you can see that at all these points momentum will be 0. Because you know momentum P is what? Momentum P is given by root over 2m times E minus V. But now you are considering such points xi where the V is equal to E. It means at those points momentum will be 0, kinetic energy will be also 0. And see the expression for the psi plus minus of x. Psi plus minus of x, which is the solution of Schrodinger equation defined in this equation 8. In the denominator there is p root over px. Now since px at those points xi is equal to 0, so when in denominator there will be 0, the result will become undefined. So in this condition you can say that this psi plus minus x will become undefined. Therefore you can say that at the points xi, since we have E equal to V of xi, therefore momentum in that very equation vanishes and the solution becomes undefined. Actually, all these points where E is equal to V of xi, all these points are called classical turning point. Classical turning point. Why these points are called classical turning point? Because classically the particle stops at these points xi and then turns back to resume its motion in the opposite direction. Okay? A particle, let us say, is moving in rightward and now it reaches to a point, let us say xn, where E and V are equal. Then at this position velocity of the particle will become 0, its momentum is 0, its kinetic energy is 0, and the particle which was moving in rightward direction, after this point it will return back. It will move in the opposite direction. And such point is actually called the turning point. Okay? In fact, at these points, the wave function, which you have actually defined here in equation 8, which I have mentioned, psi plus minus of x. Okay? And this is equal to c over root over px times e to the power I over h bar integral p of x dx. Okay? Actually, you can see, as I have told you earlier, that since at the turning points px is 0, so this psi plus minus plus minus defined here, this will become infinite. Okay. So one then needs to examine how to find the wave function at the turning point. Okay. But before looking into this fact that how we can find the wave function at the turning point, you have obtained the wave function in the forbidden region. You have also obtained the wave function in the classically allowed region. But what will be the wave function at the turning point? Okay? We have not obtained it. We will see later on in a proper problem how we can find the wave WKB wave function at the point of turning. But before that, let us first study the condition of validity for this WKB approximation. Is this WKB approximation valid always? Answer is no. There is a required condition for its validity. When that condition will get satisfied, only then you can follow or you can apply the WKB method for solving a problem. Okay? So this is a very important fact to know about the validity of WKB approximation. Okay? In fact, to obtain the condition of validity for the WKB method, let us examine the size of the various terms which you have seen by equating the real and imaginary part of the resulting equation. And in that condition, you have seen there are particularly two terms, A times del dot S, del S, gradient of S square, and I h bar A del square S. These were two terms in that equation which you have seen. I am not turning the page. Okay. When you will actually see, due to the presence of this h bar, the quantities, these quantities will be of the order of h bar or h bar square. Okay. Since h bar is very small, this is of the order of 10 to the power minus 34. So the term containing h bar will be very small. Okay. And therefore, in the classical limit, the quasi-classical region is expected to be given by this condition. It means WKB approximation will be valid when modulus of h bar del square S is much smaller than del S square, gradient of S square. Now, if you will write this condition in one-dimensional situation. So, what will be the one-dimensional equivalent of this del S? You know, del S, this is gradient of S, and its one-dimensional equivalent will be ds by dx. This is its one-dimensional equivalent, which is written as S dashed. So, S dashed is written for ds by dx, which is the one-dimensional equivalent of gradient of S. And again, this del square S, its one-dimensional equivalent will be d2s by dx square, okay, which is written as S double dashed. So you can say that h bar times this S double dashed should be much less than this S dashed square, okay, S dashed square. Or you can write h bar times S double dashed over S dashed square should be much less than 1, okay. Now this result, h bar times S double dashed by S dashed square, this can be written like this. You can check it. This is as modulus of d dx h bar over s dashed, this should be much smaller than 1. So this is the condition which, when will be satisfied, you can apply the WKB approximation. But if this condition is not satisfied, you can't apply this WKB approximation, because in that very condition, this approximation will be not valid. Now we will cast this condition in another form. You can see, we have just obtained earlier that s of x is given by plus minus integral of px, and ds by dx. From here you can see, if your aim is to find this ds by dx, you will have to differentiate this integral. But you know, differentiation is the reverse process of integration, so this will be simply plus minus p of x. Okay. So now at the place of this s dashed, see here, you can write plus minus p of x. And since this term is inside the modulus, sign of modulus, so there is no need to write plus minus that. So this result defined in equation 12 can be written as mod d dx h bar over p of x much less than 1. Okay. But what is this h bar over p of x? You know, h bar, which is reduced Planck's constant, this is h over 2 pi. So this is h over 2 pi times p of x. Okay, times p of x. Okay. This is the de Broglie wavelength. Sorry, de Broglie wavelength lambda is equal to h by p. But here there is h by 2 pi into p. So this is lambda divided by 2 pi. And therefore this is denoted by the symbol lambda bar. So lambda is h by p and lambda bar is h bar by p. And that's why this lambda bar is called, just as an analogy of h bar, this is called reduced de Broglie wavelength. As you call h bar reduced Planck's constant, this lambda bar can be said to be reduced de Broglie wavelength. So in terms of this reduced de Broglie wavelength, you can now see this condition can be written as mod of d lambda bar over dx much smaller than 1. Okay, much smaller than 1. This is the condition in terms of this de Broglie wavelength, or you can say the reduced de Broglie wavelength. You may say it. Okay. Now, actually, this condition which I have obtained here, this condition actually, what actually this condition means? Actually, the condition mentioned in equation 3 means that the rate of change of the de Broglie wavelength is small. This is d lambda bar by dx. This is rate of change of de Broglie wavelength with respect to x. And this is much smaller than 1. It means this equation implies that the rate of change of de Broglie wavelength is small. When you say that the rate of change of de Broglie wavelength is small, that means you are telling the wavelength of the particle must vary only slowly, only slightly over the distance of the order of its size. Okay? But this condition is always satisfied for classical system. So, the condition of validity for the WKB method may be given like this. This is mod of d lambda bar dx, okay, equal to d dx h bar over px, this must be much smaller than 1. Okay? This must be much smaller. So you can see this condition clearly breaks down at the classical turning point E equal to V of xi. Why? Because at this point we have seen P of xi is 0. And if P of xi will be 0, then you can see this term h bar over px will become undefined. Okay? So since pxi equal to 0, this condition will be classically the particle stops at this point x equal to xi. You know, at this point the particle will get stopped and then moves in the opposite direction, and therefore that is called classical turning point. As p of x becomes small, the wavelength which you have defined here in this equation, okay, in this equation, this will become very large. If px is small, the wavelength you can see will be large, okay, and therefore it violates the requirement that it remains small and varies only slightly when p of x is too small. Therefore, the condition which we have seen earlier in this equation, number 14, this condition actually breaks down, and so the WKB approximation is valid in both the allowed and forbidden region, but not at the classical turning point. This is a very remarkable fact. In allowed region, that is when E is greater than V of x, the WKB approximation is valid. When E is less than Vx, which is classically forbidden region, again the WKB approximation is valid. But at the classical turning point where E is equal to V of x, this WKB approximation is not valid. It means this is a very remarkable fact that WKB approximation is valid in both allowed and forbidden regions, but not in the classical turning points. Okay. So how does one specify the particle's wave function at the classical turning points? Or how does one connect the allowed states with their forbidden counterparts? As we go through the classical turning point from the allowed to the forbidden region and from the forbidden region to the allowed region, we need to examine how to determine the particle's wave function everywhere, particularly at the turning points. This is the most difficult issue of the WKB method because it breaks down at the turning point. So in the forthcoming video, we will see that the issue by solving the Schrodinger equation near the turning points x equal to xi, we will see that this calculation will become very tedious, okay, very tedious. It will not have any straightforward solution, okay. So we want to apply WKB approximation to find the energy levels and the wave function of a particle moving in a potential well, and then we will apply the formula which we have learnt. Okay? So these are the basic formalism of WKB approximation, and in our forthcoming video we will illustrate this theory by taking some important applications of it. Okay, thank you very much.